Hi everyone. In this video, we're going to look at evaluating double integrals in polar form. So here, we would like to determine how to take a double integral in rectangular coordinates. Notice we have x's and y's here, and express it using polar coordinates, r's and thetas. Now, as we'll see, the reason we'd like to do this is because depending on the shape of the region R that we're integrating over, sometimes it is easier to evaluate a double integral using polar coordinates instead of rectangular coordinates. So we'll see that with some examples, it's just much easier to use polar coordinates. Now, what we need to do here is determine what happens with the dy dx. What does that turn into when we use polar coordinates? As we'll see, it's not exactly dr d theta. There's going to be another factor in here, and that's what we want to determine. So to start, to figure out what does dy dx turn into in terms of dr's and d thetas, let's consider this diagram down here. Now in this diagram, we have a region R. Notice that we have these bounding curves. The first curve right here is theta equals alpha. This bounding curve right here is theta equals beta. This bounding curve up here, that's the bounding curve R equals G2 of theta. G2 is some function of theta. And this bounding curve down here is R equals G1 of theta. So those are the bounding curves for this region R. Now imagine that you have a z-axis coming straight out of the computer screen towards you, and that you have some surface lying above this region, so it's floating just above your computer screen, and the surface is given by z equals f of r theta. So we want to set up a double integral in polar form that will evaluate the volume of the solid lying above this region R and below this surface that's floating just above this region. So to determine what form that double integral takes, we're going to do much as what we did before when we did this using rectangular coordinates. We will partition this region into small regions delta A sub ij. So that's the way we're going to start. So you notice in this diagram here, we have the interval alpha to beta, representing what theta varies over, partitioned into subintervals of width delta theta up here. So each of these angles right here, this angle right there, is a delta theta. Each one of these angles is a delta theta. We also partition R into subintervals of width delta R. So each of these distances here, that distance, this distance, this distance, those are all a distance delta R. Now, let's consider this region right here. Now let's consider this region right here that we have shaded. Notice that point right there is r sub I comma theta sub j. And imagine that you have a little rectangular column coming straight out of the computer screen of height f of Ri theta j, right? That's going to be the height of the little rectangular column coming out of the computer screen towards you. Now the volume of that little rectangular column with base delta A sub ij is given by this right here. You simply take the area of the base times the height of your column. And then what we do to approximate the entire volume, we simply add all of these up as I indexes across its values and j indexes over its values. So you see in this picture right here, the j's, which go with the thetas, would index. You'd have like a theta 1 here, theta 2, theta 3, 4, 5, and a theta 6. And then the r would index from, or rather the i's going with the r's would index from r1, r2, r3, r4, r5, r6, r7, and r8, and it looks like you have an r9 then. Okay, so as you sum up the volume of all of these little columns with these little bases, you'll get an approximation to the volume that you want. Okay, so and this approximation, of course, becomes better and better as we let these little regions get smaller and smaller. So in the limit, as the size of our regions go to 0, our partitions, the size of our partitions goes to 0, we will get exact equality here. Now what we have to determine next is how to write this delta A sub ij in terms of delta r and delta thetas, so that when we take the limit here, this will turn into a double integral, and these will turn into dr d thetas, and then we'll have a double integral set up. Now this delta A is not exactly delta r times delta theta, as we'll see. So that's what we need to do. Now, to do that, let's take a look at this diagram. Now right here we have a blown up image of the region delta A sub ij right here. That's the pink shaded region right here. And we want to determine its area in terms of delta r and delta theta. Okay, so to do that, let's note this. The area of that region can be written like this. It's the area of the circle of radius r2. So it's going to be the area of the circle of radius r2 minus the area of the inner circle of radius r1. That would be the circle formed right here. So you take the difference of those two. Now what that will give you is the area between the two circles going all the way around. That's called an annular region. So that will give you the area in between the two circles of radius r1 and r2. That area in between here going all the way around. Now, to find the area of just this region right in here, what we do then is take this area and multiply it by delta theta over 2 pi. This is the fractional part that the delta theta is of the entire circle going all the way around. For example, if delta theta were pi over 2, then this pink shaded region would extend, like this. Okay, so that's 1/4 of the entire annular region going all the way around. And you notice if we evaluate pi over 2 divided by 2 pi, we get 1/4. And this is 1/4 of going all the way around. So if we multiply this area by delta theta over 2 pi, that will give us exactly what we want, the area of this shaded region right here. Okay, now we need to figure out what this is. Now let's notice that the radius R2 can be written like this. So the distance R2 goes from here out to here, and that can be written as this distance from the origin to here, which is R sub I, plus this little distance right here, which is half of delta R. So that distance is delta R over 2. So you see R2 is equal to R sub I plus delta R over 2. So this right here is R2. So pi times R2 squared, that's the area of the outer circle. Now the radius R1 can be written as R sub I, that's this distance again, minus this distance, which is half of delta R. So this is delta R over 2. So R1 is going to be Ri minus delta R over 2. And pi times R1 squared gives us the area of the inner circle. Now all we have to do is simplify this. So we FOIL this out and FOIL this out. Now in the next step here, notice that we pulled the pi's out and canceled them with this pi right here first. So those cancel, of course. And that gives us this right here. Notice we don't have a pi down here anymore now. And then foiling this out and foiling this out, we get this is our first term. That's this term foiled out. And this term over here gives us this with the minus distributed. Notice we have the Ri squares cancel. These two terms cancel. And we're left with 2Ri delta R. So that's right here. And then we multiply by delta theta over 2. 2's cancel, of course. And here you go. Here is the area of the region delta A sub ij. It's right here. So you notice you have that factor that I had alluded to before, Ri times delta R times delta theta. Okay, so there you go. So now in our summation that we had previously, this is what we put in place of the delta A sub ij. And let's see what we get then. Now right here we have our volume form that we had seen previously. Right here's our delta A sub ij. Now that gets replaced with this we now see. And let's write this as a double sum. Let's break this summation up as a double sum right here. So we sum over the i's first and then the j's. So the i's index over the r's. So right here we have that. Now, as the size of our partitions go to 0, this inner summation here, this will turn into an integral. This will turn into a dr. Right here we have it. This will turn into just an r, and this will turn into just an r. So that's what we have down here. Now our limits of integration, if you think of fixing the theta sub j, then the r will vary from g1 of theta j up to g2 of theta sub j, right? Let's just take a look at that picture quickly. Remember back here in our diagram, right here, if we fix theta j right there, so there's a theta j being fixed, then the r will vary from this value, which is g1 of theta sub j, out to this value right here, which is g2 of theta sub j. So that's what the r will vary from. So that's why we have those limits of integration. Let's go back down again. Okay, so we see that this summation turns into this integral with our limits of integration. And then we still have to let the delta theta turn into a d theta. This summation turns into an integral, and the theta will then vary from alpha to beta. Those are constants, as we saw in the diagram above. So once again, we still have curve to curve, point to point, and f of r comma theta. Now you notice what we have here in place of the dy dx, as we had in rectangular coordinates, we now end up with an r dr d theta. And we have now determined how to write a double integral using polar coordinates. That's what we have right here. Okay, and that's what our next theorem down here summarizes for us. So what this theorem states is that if you have a region in the form r comma theta, where r is between the two curves, g1 of theta and g2 of theta, and theta varies between alpha and beta, where the alpha and beta are fixed constants, then you can write this double integral in this form right here. And once again, notice that your dy dx became r dr d theta. Okay, so that's it. That's how we can evaluate a double integral using polar coordinates. Now let's take a look at some examples. Now let's take a look at this example. So here we have a hole of radius 3 is cored through a sphere of radius 5. Let's find the volume of the solid remaining after you remove the inner core of radius 3. So recall that x squared plus y squared plus z squared equals 25 is the equation for a sphere of radius 5. And then coring a hole of radius 3 through this sphere, or rather through the upper hemisphere of this sphere, is going to result in a solid as we have shown below. So here we have the upper hemisphere of our sphere, and you see we have a hole cored through it of radius 3. Notice that this is 3 on the y-axis and 3 on the x-axis down here. Also notice that this is 5 on the y-axis. That's where our sphere cuts through the y-axis, and 5 on the x-axis over here as well. And the equation for the upper hemisphere we can write as z equals the square root of 25 minus x squared minus y squared. And keep in mind that to convert this into polar coordinates, remember that x squared plus y squared equals r squared. That's one of our conversion equations for rectangular to polar coordinates. And so we can replace this right here with minus r squared. And so there is our equation for the upper hemisphere in polar coordinates. Now the region R that we want to integrate over is the annular region between these two circles of radius 5 and 3 in the xy plane. That's the region over which we're going to integrate. So now let's set up our integral in polar form that will evaluate the volume of this resulting solid that we have pictured here. Now keep in mind we're then going to have to multiply our result by 2 because we only have the upper hemisphere pictured here. So what we get is this. So here's the region over which we're going to set up our double integral. Now notice that the radius r varies from 3 out to 5. So this curve right here is the curve r equals 3, and this is the curve r equals 5 out here. And so the volume of that hemisphere is going to be this double integral. Now notice right here is our f of theta comma r, square root of 25 minus r squared, and right here is our dr d theta. Now what does the r vary from? Well, we see that the r varies from 3 to 5, curve to curve. 3 to 5. They just happen to be constants in this case. And then the theta will vary from theta equaling 0 all the way around to 2 pi. So the theta varies from 0 to 2 pi. And there you go. This is what we have to evaluate. So now integrating this right here with respect to r, the antiderivative of r times the square root of 25 minus r squared, that is right here, is just a simple integration by substitution. You can easily do this in your head. You notice that r times 25 minus r squared to the 1/2 power. Now if we integrate this, you're going to get 25 minus r squared to the 3/2 power, adding 1 up here. And then just realize that you're going to have to multiply this by 2/3, because when you drop this 3/2 down, you are going to cancel it with a 2/3. When you differentiate the inside, you're going to pick up a negative 2r, but you don't want negative 2r, you just want an r. So you multiply this by negative 1/2. And so that's how we get negative 1/3, 25 minus r squared to the 3/2 power. So right here is the antiderivative for this right here. Or of course, if you want, you could do a substitution right here with u equaling 25 minus r squared. So right here is our antiderivative, evaluated from 3 to 5. Put 5 in here for r. Of course, you'll get 0. Then put 3 in here for r and subtract, and you will end up with 64 over 3. You can double check that. Just put the 3 in here. That minus will go away. And then we just have to integrate this from 0 to 2 pi with respect to theta. Well, of course, this is just going to be theta times 64 over 3 evaluated from 0 to 2 pi. Put 2 pi in here for theta, 0 in here for theta, subtract, and here you go. There's your answer. Now, of course, we only found the volume of the upper hemisphere with the whole of radius 3 chord through it. So if we want the whole sphere, we need to multiply this by 2. That's what we have right here. And there is our answer, 256 over 3 pi. And so now you see why we wanted to use polar coordinates for this problem, because when we use polar coordinates, notice how nice our limits of integration turn out to be. And we have a nice integral here to evaluate. It's not that difficult. If we had done this in rectangular coordinates, it would have been much more difficult. Let's take a look at another example. Now here we want to evaluate this double integral over the region R, which are the values r and theta, where r is between 1 and 4, and theta varies from 0 to pi over 2. So we want to evaluate this double integral over this region. Now this double integral represents the volume of the solid that we have shown down here, and the region R is shown over here. So let's take a look at those. So here is the surface z equals x plus y that's in the integrand of our double integral. So that's just a plane. And down here in the xy plane, the gray shaded region down here is the region R over which we're integrating. And so that double integral represents the volume of this wedge-shaped solid. Now notice that the region R over here, the radii R, they vary from 1 out to 4. So this is R equals 1, and this is R equals 4, those two curves. And then the theta varies from 0 to pi over 2. Okay, so also notice that this equation up here, we're going to have to convert this into polar coordinates. The x, of course, is r cosine theta. And the y is r sine theta. And so we can represent this in polar coordinates like this. Okay, now let's set up our double integral. So here we have our double integral. Notice that x plus y, that is r cosine theta plus r sine theta. The dA, that becomes r dr d theta. Now the r, that's going to vary from 1 to 4, r equals 1 to r equals 4. And then the theta, as we've seen, will vary from 0 to pi over 2. So once again, these are curve to curve, and then point to point. All right, so now just evaluating this isn't too bad. Let's just factor the r away from these two terms, and so this r right here becomes an r squared. Now we want to integrate this with respect to r. So we treat these thetas like constants, so what's inside the parentheses here is just a constant. So the antiderivative of this with respect to r is going to be r cubed over 3, and then we just bring down the cosine theta and sine theta, treating them like constants. This needs to be evaluated from 1 to 4, so put 4 in for r, 1 in for r, and subtract. And this part right here will become 63 over 3. So that's just a constant. We can pull it out in front of the integral. And now we just need to find the antiderivative of this with respect to theta and evaluate it from 0 to pi over 2. Antiderivative of cosine is sine. Antiderivative of sine is negative cosine. Put pi over 2 in for theta. Put 0 in for the thetas and subtract. and you will get 2. 2 times 63 over 3 gives us 126 over 3, and there's the volume of that wedge-shaped solid. And so there you go. There's another example using polar coordinates. And you notice that this problem, because of the shape of the region R, it was much easier to use polar coordinates than rectangular coordinates. Now for this next example, let's note that if we let the function f of r comma theta equal 1, then the double integral with this f equaling 1 is just going to give us the area of the region R that we're integrating over. So we can use this to evaluate the area of a region R. Now let's take a look at this example. So let's evaluate the area bounded by this lemniscate. R squared equals cosine of 2 theta. Now down here we have the graph of what that looks like. So here is the graph of r squared equals cosine of 2 theta. Notice that we can write this as r. This would be r equals plus or minus the cosine of 2 theta square root of that, right? Okay. So if we start out with theta equaling 0, if we put 0 in here for theta, cosine of 0 is 1, so we start out right here. Now as we let theta vary from 0 to pi over 2, notice that once we get to pi over 4, 2 times pi over 4, that's going to give us pi over 2, and that's when the cosine is equal to 0, right? So if we start out with theta equaling 0, by the time we get to pi over 4, the term inside here will equal 0, and we will be back here at the origin. So this angle right here, that angle right there, is pi over 4, because when we put pi over 4 in here, we get the cosine of pi over 2, which is 0. So if you were to plot this out, you see that when you start out with theta equaling 0, by the time theta is pi over 4, you're back at the origin again. So this is one branch of your lemniscate, and that's for theta going from 0 to pi over 4. Now when we set up our double integral, we're only going to evaluate this area right here. So then if we want the area inside the entire lemniscate, then we need to multiply that by 4. So now let's take a look at our setup for the double integral. So you see right here we set up our area. It's going to be 4 times, and we have our double integral. Notice we have a 1 in here, and we're multiplying by 1 times r dr d theta. The r varies from 0 to the square root of cosine of 2 theta. You know, if we look back at the graphic up here, just notice that right here, over this shaded region in here, r goes from 0 out to that point on the curve, and so this distance here is, if this is theta, this distance is the square root of the cosine of 2 theta, right? That's your r. So r is varying from 0 out to the square root of cosine of 2 theta. So that's how we get these limits of integration right here. And then theta, you see, will vary from 0 to pi over 4. So here is our double integral, and we just need to evaluate that. And so evaluating this, we integrate with respect to r first. Antiderivative of r is just r squared over 2, evaluated from 0 to the square root of cosine 2 theta. So we put this in for r, 0 in for r, and subtract. And that's sort of nice because we're taking the square of the square root, so the square root disappears, and we end up with 1/2 cosine 2 theta. Integrate that with respect to theta from 0 to pi over 4. Antiderivative of cosine 2 theta is sine 2 theta over 2, right? The antiderivative of this is sine 2 theta, and then we need to multiply that by 1/2 to counteract the 2 here if we were to differentiate. And so 1/2 times 1/2 gives us the 1/4 right here. That's where that 1/4 is coming from. And then we are multiplying by 4, so of course this all cancels right here. And then we just have to evaluate the sine of 2 theta from 0 to pi over 4. Put pi over 4 in here for theta, 0 in here for theta, and you'll get 1. And there you go. So that is the area inside of this lemniscate right here. So that's the total area inside here. Total area in here is 1. And that concludes our discussion about double integrals in polar form.